Oh boy, do we have a monster topic tonight, trapezoidal approximations. And just to go ahead and clarify our goal is to approximate the numerical value of a definite integral. Okay, so it's very similar to what we saw yesterday with the Riemann sums and all those rectangles. We did a right-handed rectangle and a left and a midpoint. And today we're going to add a fourth approximation method called the trapezoidal. And I think you're going to find that the trapezoidal is indeed the most accurate, at least 90% of the time. It's crazy how little amount of wasted space there really is. But just to clarify a couple of the definitions we introduced yesterday, a definite integral. Do you remember how we clarify the difference between a definite and an indefinite? Well, a definite integral is one that's got bounds. And what it does is it establishes a finite space between some function in the x-axis and then the vertical lines x equals a and x equals b. So if we just graph this out really quick, maybe there's f, there's a, there's b, and we're measuring all the space in between that. There. So the answer, the output to that problem would be just some number, and what that number does is it's measuring the area of that space. Compared to that, an indefinite integral is one that does not have bounds on it. We're just simply integrating a function. And in other words, I want you to think like we're trying to find that function's antiderivative. So just to give you an example here, if we were integrating x squared with respect to x, the antiderivative would be 1/3 x cubed plus c. And we'll talk about that mysterious c later, but just to clarify the difference between those two integrals. Now, I've always thought that the trapezoids are one of the more fun geometric shapes to work with and analyze and so forth, and they're certainly not very boring. They've got a lot going on. But what I've brought into the screen here is a very well-behaved trapezoid. We call it an isosceles trapezoid because these non-parallel sides here are congruent to each other. So that just to help us establish the area, we said basically it was the average of the bases. In other words, you're going to add base 1 to base 2 and then divide by 2. So there's the average of the bases, and then we simply multiply by the height and you've got your area. Now even when the trapezoids weren't as well behaved, and you'll notice here that this one's not isosceles, our non-parallel sides are certainly not congruent, the same formula applied. We had a long base 1 here, shorter base 2, and then actually this one was easier to grab the height. It was easier to find because it was just simply the length of that one side. But what we're going to do here today is we're going to grab that trapezoid and, whoa, hold on, don't move there. Okay, better not try that. We're going to basically rotate that trapezoid 90 degrees, just like you're turning a door handle a little bit, and we're going to use this image right here. And so we're going to just clarify some of our terms. We're going to say that we've got a height 1 right here that measures the length of this height, and then the other height over here we're going to call it h2, and then across the bottom is going to be our base. So our formula today, we're going to say the area of our trapezoids is the average of the heights, all right, times the base. And that's the formula that I want you to now visualize and imagine for our trapezoids that are going to be oriented more upright. They're going to be tall and skinny today. Alright, our first live example is we're going to stick with the same function that we worked with last night, 25 minus x squared. So we've got this very nice polynomial. Polynomials are always guaranteed to be continuous and differentiable. They're so nice to work with. Of course, we had our y-intercept of 25 and our x-intercept of 5, but the integral is only measuring the area from 0 to 4, so 1, 2, 3, and 4. And they wanted us to create two subintervals. So the first subinterval is going to have a base of 0 to 2. And what I'm going to do is I'm going to extend my first height all the way up to 25, and then my second height is going to be f of 2. And then at the tip top there, I'm just going to connect those two peaks. And you'll notice very little wasted space at the top, or a slight underestimation. But anyway, so the area of this first one is going to be 1/2. Now I'm averaging my two heights, so f of 0 represents the first height right there, and f of 2 represents the second height, and I'm going to multiply that by my base of 2. Conveniently, the 1/2 and the 2 are going to kill each other, and my area here is going to be 25 plus 21, and let's see, we got a grand total of 46. Now, as far as our second trapezoid, I've got a base that starts at 2 and ends at 4, and I'm going to extend the first side up, extend the second side up, and then we'll just connect those peaks. Again, very little wasted space. This is a great approximation, and we only have 2 subintervals. One of our big themes yesterday was we did see that the more subintervals we use, the more accurate our answers become. So you can just imagine, and once we use 4 or 10 or 20 subintervals, how crazy accurate this is going to be. But anyway, we're going to say f of 2 represents that first height, and f of 4 represents the second height, and the base is 2, so boom, boom. Let's say we've got an area, let's see, 21 plus 9, that's going to be 30 units. Add the 2 trapezoids together, we've got a grand total of 76 for our area. Okay, I do want to try setting one up with 4 subintervals here within the same integral. You know, I just want to keep the integrals similar so we know we're comfortable with that. And we'll bust out a few extra colors here. Anyway, so the first one is we've got a height of f of 0 and a height of f of 1. That's what I really want to focus on, is getting the correct heights here. So the very first trapezoid is going to be 1/2, and the heights are going to be f of 0 plus f of 1, and a base of only 1 unit. Alright, now the second trapezoid, we've got a height of f of 1 right there, and then a height of f of 2 right there. Connect them at the tip top. So we've got 1/2 f of 1 plus f of 2, and the base is 1 unit. Okay, what do we got cooking here? Let's do our third trapezoid's got a height of f of 2 and then f of 3. Connect them. Very, very good approximation. Very little wasted space. So we've got f of 2 plus f of 3. And of course, when I say f of 3, all I'm doing is I'm substituting a 3 into this function right here. I'm considering that my f of x. And last but not least, let's grab maybe some pinkish color here. F of 3 is my first height, f of 4 is my second height. Connect them, and here is my fourth and final trapezoid. So they're not too bad. Very little, just a little bit of number crunching, nothing too strenuous. Add all those 4 areas together, and boom, you've got yourself a great approximation. I also wanted to go back to another picture that we were familiar with and comfortable with from yesterday, and that's this goofy curve called f of x. And let's see if we can create the 3 trapezoids that they are looking for. If we're going to go from -2 all the way to 4, we're thinking -2 to 0 is our first interval, 0 to 2 would be our second, and 2 to 4 would be our fourth interval. So if I start at -2 and go to 0, and I'm going to extend the -2 all the way up, there's my first height, and then the 0 goes all the way up, and then I connect the 2 of them, and compare that to the rectangles we had yesterday. This is a really good approximation. So the first area, I'm thinking we've got 1/2. The heights are, let's see, f of -2 is 5, and f of 0 is a 1, and then my base is 2 units. So I think I got a grand total of 6 for my area. All right, the next one's going to go from 0 to 2. Got a height there, and my second height is f of 2. Connect those with a straight line, and let's see what we got. We got 1/2. The first height was 1, the second height was a 5 again, and the base was 2. Looks like I got the same size trapezoid with another area of 6. And then last but not least, we've got a height at f of 2. We've got at 4 we've got a height of 0, so we connect them, and we actually created a triangle in essence, because let's see, we've got a 5 plus a 0 for my heights, base of 2, and area of 5. So it looks like 17 is going to be my total combined area. In other words, that's the numerical value of this definite integral that bears whoops, don't use equals, use an approximation. It's approximately 17. So hopefully so far tonight you've been cooking right along. I mean, really all we had to do was to go back to our middle school days and refresh ourselves on what a trapezoid looked like, what its formula was, and probably the only tricky thing that we really did was we rotated that trapezoid 90 degrees so that it was standing tall and upright. But other than that, really it's just the conceptual understanding of what this trapezoid is attempting to do and how it's a very good approximation for measuring a definite integral, which of course measures the exact area bounded between a curve and the x-axis. So tonight I want to finish the video by extending into some word problems and looking at some typical AP questions, just so you know where we're kind of going with this topic. And so I want to have a quick discussion on units, believe it or not. Yeah, that's where we're going to go. We're going to talk about units. And what I want you to do is I want you to imagine some random function. We'll call it f of t. F of t is measured in, we'll say, feet. So it's some mysterious function measured in feet. And if we wanted to derive that function, if we derived it, we would start to, we'd use notation. We'd say like f prime of t, and it would now be feet per, say second, or minutes or hours or some unit of time. And then if we derived, if we derived that function, we would say feet double prime, f double prime of t, and it would now be measured feet per second squared. All right, that's why we really want you to focus on this, because every time you take a derivative, you're doing another rate. And every time you have a rate, it's something per unit of time, okay? So every derivative we take, if I took the third derivative, it would be feet per second squared. Now cubed. If I took a fourth derivative and I started using Roman numerals for my notation, it would now be feet per second to the fourth. Now, and I have no idea what that means, I know feet per seconds, typically velocity. I know feet per second squared is typically acceleration. When the physics folks will tell you that feet per second squared is something they like to call jerk. In other words, the rate at which the acceleration is changing. But this last one, I have no idea what it means, but I just wanted to throw it out there just to emphasize the units. Now let's turn that on its head and let's talk about integrating per se. All right, so if I wanted to integrate a function that was feet per seconds to the fourth, remember integrating is doing the opposite of what a derivative does. That's why we call it an antiderivative. And so the new units on your new function would be feet per second cubed. And if you integrated that, you would get a new function that was measured in feet per second squared, aka acceleration. And if you integrated acceleration, feet per second squared, you'd get a new function called feet per second, aka velocity. All right, let's see. If you integrated that function that was measured in feet per second, you'd get a new function that was measured in strictly feet, aka your position function. Here's where it gets a little bit weird. If you integrated feet, you would now get feet seconds. Not feet per second, but feet seconds. In other words, think of it this way. Every single time that we integrated, what we essentially did is we multiplied by seconds. You can think of it that way. We multiplied by seconds. And I think if you think of it that way, it makes a little more sense how you could get feet seconds instead of feet per second. But we'll add a little bit of meaning to those as we go here. So here we go. Here's a very typical AP problem. They said during the time interval of 0 to 12 hours, water was pumped into a swimming pool at the rate shown in these tables. But so P of T is measured in cubic feet per hour. And, strictly monotonic just means, monotonic means it's either only increasing or only decreasing. So you kind of takes away some of the unknown erratic behavior that may exist in these tables sometimes. So monotonic means these numbers are strictly increasing. There's no wild spikes that exhibit decreasing behavior. And it is differentiable, so that's going to help. And the first thing they want us to do is explain the meaning of this first definite integral. In fact, I'm going to cross off. I'm not worried about the second one yet today. But yes, we do have ourselves a definite integral. It's got bounds. It represents a numerical value. And we're going to approximate that numerical value. But before we do that, I want to explain the meaning. If I integrated a function, P of T, that was measured in cubic feet per hour, I would get a new function that was just cubic feet. So what this does is this definite integral is measuring the total amount of water pumped into the swimming pool between t equals 0 and t equals 12 hours. Pumped into the swimming pool between, and this part's just as important as any of it, between t equals 0 and t equals 12 hours. And I should have included here the total amount of water in cubic feet. That unit right there is just as important as well as anything else. Okay, now they wanted us, now this is a little bit of a flashback to yesterday. The first one they want us to use is a midpoint Riemann sum with equal intervals, with 3 equal subintervals. So what I'm thinking is I'm going to go, kind of formalizing my plan, I'm going to go 0 to 4, and then I'm going to go 4 to 8, and then I'm going to go 8 to 12 to finish it off. And this is just the rectangle, so it's strictly base times height. The first rectangle goes from 0 to 4, so the base is 4 units. And I'm going to use the height at its midpoint, which in this case is 12. Okay. The next rectangle goes from 4 to 8, and that's got a base of 4. And I'm going to use his height at 6, which is 25. Again, 6 was the midpoint of the base, and so we go with his height. And the third rectangle goes from 8 to 12, so there's again a base of 4 units. And the midpoint of the base is 10. His height is 50. And if we just simply multiplied and added all those rascals together, we would have a numerical approximation. So let's go ahead and do that just for fun. 48 plus 100 plus 200, that's going to give us 348 what? Cubic feet of water has been pumped into that pool between t equals 0 and t equals 12 hours. Now, what I want to do before I abandon this particular problem is I wanted to revisit a right, a left, and also introduce you to the trapezoidal one here really quick. If we did a right Riemann sum instead of a midpoint, and assuming we're going to do 3 subintervals again, I would still have a base of 4 units, but which height would I use if I was doing a right? Well, the right edge of the base is at 4, so the height would be 20. So I would go with 20. Then I would go 4 to 8 and use a height of what? Hopefully you said 30. And then the last rectangle would go from 8 to 12 with a height of 55. So again, focus on your heights. And if we're doing a right Riemann sum, make sure that you agree with those heights. Let's go ahead and do a left really quick. And go ahead. It's a great time to hit the pause button and make sure that you could set up your left Riemann sum really quick. And then come on back, see if we agree. All right, my first rectangle, 0 to 4, so it's a length of 4. And I'm going to go with the left edge whose height is 0. So nothing cooking there. And then from 4 to 8, I'm going to use the height of 20. And then from 8 to 12, I'm going to use a height of 30. That's the height of the left edge of the base of that rectangle. Okay, one more really quick. Let's go ahead and talk about our trapezoids because that's our big theme today. So above all else, we want to make sure we do the trapezoid. 3 subintervals, and so I'm thinking I'm going to go 1/2. Now, if my base is 4 units, height 1 would be 0, and the 20 would be height number 2. So I'm going to go 0 plus 20 with a base of 4 units. And then for my second one, I'm going to go 1/2, and now I'm going to use the 20 and the 30 as my respective heights, still with a base of 4. And for the very last one, we're going from 8 to 12, so I'm going to use 30 and 55 as my respective heights. 30 plus 55 multiplied by a base of 4. So really, I mean, the number crunching would slow us down a little bit, but certainly nothing we're not capable of doing, and they would expect us to do this number crunching on our own. Whatever you get done, you would have some beautiful number, and the units would be cubic feet, because again, it represents the total amount of water that's been pumped into that pool. Okay, we've got ourselves a new function, new table, new numbers to play with. And like I said, the AP loves tabular type of problems. Just tabular comes from the root word table. And so we've got, we're referring to a school carnival where we sold some raffle tickets for a fundraiser between t equals 0 and t equals 8. The number of raffle tickets sold is modeled by function r. Now this is certainly different than the last problem where the function they gave us was already a rate, it was cubic feet per hour that the water is being pumped in. This function doesn't represent, it's not number of raffle tickets sold per hour, it's just total number of tickets sold, t hours from now. So anyway, let's just jump in and see if we can't figure out the trapezoidal sum to measure this integral right here. And we're going to go 4 subintervals, so we're going 0 to 2, but we were using the ones designated in the table, so they're not going to be equal. All right, not equal intervals, just because we don't have a choice. We just have to go with the information we have in the table. So my first trapezoid has a base of 2 units. And the respective heights are going to be 0 and 5. 0 on the left edge, 5 on the right edge. Okay, my second is going to go from 2 to 5. So that's a base of 3 units. And my respective heights are 5 and 9. All right. The third trapezoid is going to go from 5 to 6. So my base is only 1 unit. My respective heights are 9 and 10. of those edges. It's just trying to visualize. It's almost like trying to visualize plotting these points, and maybe drawing a logical curve that connects those points, and then visualize your trapezoids underneath those. Okay, our very last trapezoid, our fourth one, is, let's see, it's going from 6 to 8. So we're back to a base of 2, and the respective heights are 10 and 11. And again, we could do the number crunching and crunch it out. But what I wanted to focus on here on our last question was, is this an under, or I should say an over or an underestimate? And it all goes back to the function's concavity actually tonight for trapezoids. It's very unlike the rectangular Riemann sums, where it was all about, depending on whether the function was increasing or decreasing, and that was it. Well, what we've got here is we've got a function, because r double prime's negative, that implies that r itself is always concave down. And if you visualize that concave down curve, and you visualize a trapezoid that's connected right there, it's going to be an under approximation every time when the concavity is down. So there it is, ladies and gentlemen. We talked about a lot of trapezoids tonight. We did sneak in some review of the rectangles, and we talked about some interpreting the meaning of some of these definite integrals and focusing on the units to do so. So good luck, and we'll see you tomorrow.